In this lecture, we're going to see how sometimes double integrals can be made much more simple when we express them in terms of polar coordinates. That's especially going to be the case when there's some sort of circular symmetry or rotational symmetry in the problem. At the end of this lecture, I'll show how these ideas can be extended to any coordinate system. But in this course, we're really only going to focus on two: the Cartesian coordinates, x and y, and the polar coordinates, r and theta. So let's quickly revise polar coordinates. So we have a coordinate r and theta, the polar coordinates, and they're related to the familiar Cartesian coordinates x and y by this formula. X is r cosine theta, y is r sine theta. And we can transform back as well. R is equal to the square root of x squared plus y squared, and theta is equal to the arctangent or the inverse tangent of y over x. So let's prove these results, and then we'll see how we change double integrals when we use polar coordinates. So if I was to sketch the polar coordinate system and relate it to the Cartesian coordinate system, I would draw something like this. Here's my x and y. And by r and theta here, I mean the distance from the origin and the angle with respect to the x-axis. So r is the distance from the origin, and theta is the angle with respect to the x-axis. And we can express this either as xy, this point here as xy, or as r theta. Either of those pairs of numbers is enough to specify that point, as long as I know which coordinate system I'm looking at. So we want to have a way of moving between these two coordinate systems. To get x and y from r and theta, it's straightforward. We just use the trigonometric formulae. So y, the opposite side of this right angle triangle, will be given by the hypotenuse r times the sine of the angle, and x, the adjacent side, will be the hypotenuse times the cosine. So we have the relationship that x is equal to r cosine theta and y is equal to r sine theta. And we'd also like to be able to go the other way. So given x and y, how do we figure out what r and theta are? So we can actually manipulate these formulae, x and y, to get expressions for r and theta in terms of x and y. So the first thing I'm going to do is I'm going to add together x squared plus y squared. So I know that x squared is r cosine theta, and I know that y squared is r sine theta. Squaring each of these terms gives me r squared cosine squared theta, r squared sine squared theta, and I can take out the common factor of r squared. I get cosine squared theta plus sine squared theta, which of course is 1. So that gives me r squared. So I can rearrange that now to get r is equal to the square root of x squared plus y squared. And of course I'm taking the positive square root there because r is a positive number, it's a distance. So that's how I get r in terms of x and y. What about theta in terms of x and y? Well, again, I can manipulate my expressions. Let's look at y over x. Substitute in the expressions for y, r sine theta, and x, r cosine of theta. You see that the r's on the top and the bottom cancel out. I've got sine over cosine, which is tangent, tan of theta. And then I can invert that to get an expression for theta. So that gives me theta is equal to the inverse tan of y over x. So given a value of x and y, I can calculate r and theta. And likewise, given a value for r and theta, I can calculate x and y. So these are my polar coordinates and their relationship to the Cartesian coordinates. How can we make use of these coordinates now to calculate integrals? Well, we're going to see that the most important part of that is the fact that my infinitesimal area has a slightly non-trivial expression in terms of r and theta. So let's take a look at that. So I'm trying to find a little infinitesimal area dA, and it's going to be made up of two pieces. It's going to be made up of the angle and a little distance. So thinking about what this shape looks like, this is supposed to be a d theta there, sorry about that. You can see that I've got a little pi wedge here. If I have an infinitesimal angle, I've got a little pi wedge, I've got a distance r, and then I've got an extra little bit added onto that distance, dr. So to be able to calculate this area, I'm going to approximate it as a rectangle with one side of length dr, and one side given by the arc length subtended by this angle, d theta, and this distance, dr. So again, slight little error here, that should be a d theta. That angle d theta subtends an arc length of r d theta. So this rectangle, or approximate rectangle, has one side of length dr, one side of length r times d theta, and so the area will be the width times the breadth, which is r d theta times dr, or r dr d theta. And it's important here to remember that when I'm putting in my infinitesimal area, let's just remember what that looked like in terms of dx dy, or dy dx. The difference here is that we don't just have dr d theta like you would for dx dy or dy dx. We need to have this extra factor of r. So this is really important. So we're going to have to remember that as we go through these calculations. So apart from that, it's just relatively straightforward to calculate double integrals. So let's first of all get a little bit of practice here calculating polar coordinates, and then we'll do a double integral involving a polar coordinate question. So first example here, we want to find the polar coordinates of a point given Cartesian coordinates. So we're going to use our expressions here. R is equal to the square root of x squared plus y squared. The Cartesian coordinates are 1 and root 3. So we've got the square root of 1 squared plus root 3 all squared. So I've got the square root of 1 plus 3, square root of 4, which is 2. I also want to find the angle theta. So this is going to be the arctangent of y over x. Put in y and x there. We're going to get a square root of 3 divided by 1, or the square root of 3. And so that's going to be the arctangent of square root of 3 is pi over 3. And we have to think about the sign there a little bit, because if I draw my little all students take calculus, or another stupid trig catchphrase, however you learned it, we see that the quadrant that we're looking at here is the first quadrant. So all of my sines, cosines, and tangents are positive, so we have the positive pi over 3. So let's look at calculating Cartesian coordinates from polar coordinates. We're told that r is equal to the square root of 2, and theta is equal to 3 pi over 4. And the first thing we should do is figure out where exactly on the in the unit circle is this. So we know that this is the angle theta is equal to 0. Here we've got theta is equal to pi over 2. Pi over 2. theta is equal to pi, theta is equal to 3 pi over 2, and theta is equal to 2 pi, would bring us back to the very beginning. Now, where is 3 pi over 4? Well, that's going to be halfway between pi over 2 and pi, so that's right here. So the angle 3 pi over 4, let's put it in blue, is this angle here. And this means that this angle lies in the second quadrant. So again, all students take calculus. This means that my sine is going to be positive and all of the others will be negative. So cosine will also be negative. To calculate the sines and cosines, I'm actually going to make use of the remainder angle here. So this is the angle pi over 4. So that's pi minus 3 pi over 4. So we can see that sine of 3 pi over 4 will be plus sine of pi over 4, and cosine of 3 pi over 4 will be equals to minus cosine pi over 4. So now we're ready to calculate x and y. So x is equal to r cosine theta. R is equal to the square root of 2. Theta is equal to 3 pi over 4. We saw that cosine of 3 pi over 4 was minus pi cosine of pi over 4. So that's going to be equals to the square root of 2 times minus 1 over root 2. And that whole thing is going to be equals to minus 1. That leaves us with y equals to r sine theta. We saw that the sine of 3 pi over 4 is the sine of pi over 4, which is 1 over root 2. Root 2's cancel out, so I get plus 1. So I get the point x is equal to minus 1, y is equal to 1. Now, in the last example here, we're told to express an equation in terms of r and theta in Cartesian form. So I want to express this in terms of x and y instead of r and theta. Okay. Now, what I could do here is simply try and substitute in x and y and try and figure out what that expression is. But in fact, that's not the most straightforward way to do this. Instead, what I'm going to do is a little trick. I'm going to multiply both sides by r. So here's my original equation. Let's multiply both sides by r. And see if I can figure out from the resulting expression what it would look like in terms of r and theta. Excuse me, in terms of x and y. So you notice that I've got r squared on the left-hand side. Well, I know that that's simply x squared plus y squared to the distance from the origin. And I've got an r cosine theta. Well, that's x. I know that from the relationship between x, r, and theta. Okay, so now I have an expression x squared plus y squared equals to 2x. And that is an equation for that curve in terms of x and y. But in fact, I'm going to go a little bit further because I'd like to be able to interpret what that curve actually is. I'm going to do that by bringing that factor of 2x over to the left-hand side and completing the squares of the resulting expression. So you notice here I've got x squared minus 2x. That's actually the same thing as x minus 1 squared minus 1 plus y squared is equal to 0. So what I did there was I used the fact that x minus 1 squared minus 1 is equal to x squared minus 2x. Now, if you didn't see that, what you can do is you can write x squared minus 2x as x minus a all squared plus b. Multiply it out and figure out what a and b are by matching up the terms. So I'd have x squared minus 2ax plus a squared plus b. By matching up the terms, you see that a must be equals to 2, because it has to correspond to this term here. And a squared plus b must be equals to 0. So what we have is a equals 1, because 2a has to be equals to 1. 2a has to be equals to 2. And a squared plus b equals 0, which gives me b equals minus 1. So you may have your own method for completing the squares. This is how I do it. And one way or another, it ends up with this expression here. Now you notice that I can take that factor of 1 over to the right-hand side. And now I can interpret what this curve actually is. This is a unit circle, so a circle with radius 1, centered at the point x is equal to 1, y is equal to 0. Okay. So this curve in polar coordinates has this expression in Cartesian coordinates. So now let's take a look at a double integral involving polar coordinates. When we're going to be given this integral in terms of x and y, and we're going to be given the region of integration, and we're going to see that that has a very simple expression in terms of polar coordinates. First thing we're going to do is do the integral in terms of Cartesian coordinates, then in polar coordinates, and see that they're both the same thing. So let's first of all sketch our region of integration. We're told that it is all the points in x and y such that x squared plus y squared is less than or equals to 1, so within the unit circle, and for positive values of x and positive values of y. So in the first quadrant. So let's sketch what that looks like. So we're looking at points inside the unit circle. So let's sketch x squared plus y squared is equal to 1. And it's in the positive x and positive y quadrant. So here's y is equal to 0, so it's above that line, and here's the line x is equal to 0. So it's to the right of that line. So it's clear that the region of integration then is this region here. Now it's pretty clear that the region of integration here has some sort of circular symmetry, so polar coordinates make a lot of sense. But we're actually going to do this integral first of all using Cartesian coordinates. So let's see what that would look like. We're actually given the integral as dy dx, so my region of integration is going to be given by omega, the green shaded region, and we're going to carry out that integration by doing the y integral first and then the x integral. So x is the outer limits of integration, y are the inner limits of integration, the any inner variable of integration. Okay, so x is the outer variable. So we need to find the largest and smallest values of x. And you can see that x is going to go between x is equal to 0 and x is equal to 1. So let's sketch those. We've got the point 0, 0. We might as well put in these points as well. So this is the point x is equal to 1, y is equal to 0. This is the point y is equal to 0, x is equal to 1, y is equal to 1. X equals to 0, y equals to 1. So x is going to start off at 0 and then it's going to go to 1. So we're going between x is equal to 0, x is equal to 1. We're going to pick a value of x between those, and then we're going to go from y is equal to 0 and go all the way up to y is equal to whatever this curve is. So we need to express that curve as an expression in terms of x, and you can see that it's the unit circle, so it's x squared plus y squared equals to 1. And so I need to express that in terms of y as a function of x, and that's going to be given by the square root of 1 minus x squared. So y is going from 0 to the square root of 1 minus x squared. So my integral now is going to be given by the following expression. The integral from x is equal to 0 to x is equal to 1, y is equal to 0 to y is equal to 1 minus x squared, and my integrand was 3x. I'm doing the y integral first, then I'm doing the x integral. So we can do that y integral, treating x like it's a constant, putting in the limits of integration from 0 to the square root of 1 minus x squared. If I put those in, I'm going to get 3 times x, substituting in y is equal to 1 minus x squared. And I can also substitute in y is equal to 0, which will give me 0. So the integral I need to do is this integral. Now this is an integral we can do by a substitution. I'm going to make the substitution u is equal to 1 minus x squared, which gives me du is equal to minus 2x dx. And u at x is equal to 0 is 1, u at x is equal to 1 is 0. So making that substitution, we get the integral from u is equal to 1 to u is equal to 0. I know that x dx is going to be minus a half du, so I can put that in. 3 over 2 du, the square root of u. So if I manipulate this a little bit, I can flip the order of integration. So I go from integral from, not from 1 to 0, but I go from 0 to 1, and I can always do that by changing the sign. So that gets rid of that minus sign. I can take out that factor of 3 over 2. I've got u to the power of a half du. Doing that integral gives me u to the power of 3 over 2 divided by 3 over 2, which neatly cancels out that 3 over 2 outside. That's going to give me 1 to the power of 3 over 2 minus 0 to the power of 3 over 2, which is equal to 1. So this integral was doable using Cartesian coordinates, but it did involve using a substitution variable. Let's now show that that same integral can be done very simply indeed using polar coordinates and exploiting the fact that this region of integration has a nice circular or rotational symmetry. So let's sketch once again the region of integration and try and express the limits of integration now in terms of r and theta instead. So here's y, here's x. Here's my unit circle in the positive x, positive y quadrant. I'm looking at positive x and positive y. So it's this little pi wedge, this quarter of a circle, shown in green. Okay. Now, how do I express all of this in terms of polar coordinates? Well, let's sketch where the polar coordinates will be. So I've got a line going from the origin to the radius r is equal to 1. So r can take any values between 0 and 1. And theta will be the angle with the x-axis, and theta can vary between 0 and pi over 2. So theta is equal to 0 to theta is equal to pi over 2. Okay, so what are the limits of integration in polar coordinates? Well, they're very simple. We've got r going from 0 to 1, and I've got theta going from 0 to pi over 2. So you notice that immediately there's a difference between the limits of integration in polar coordinates and the limits of integration in Cartesian coordinates. Let's just flick back up those for a second. You notice that in Cartesian coordinates, my limits of integration for y, the inner integration variable, depended on the other variable. So that actually made my integral a little bit more complicated. In this case, however, in polar coordinates, my two limits of integration, my two variables, actually don't depend upon each other. So what that means is that the integral is going to become very simple. And in fact, I can do the integral in whatever order I like. So let's do the integral with respect to r first and then theta. But again, it doesn't matter because the limits of integration don't depend upon each other. So I have to put the integral with respect to, I'm going to do the integral with respect to r first, so 0 to 1. And then with respect to theta, so 0 to pi over 2. I need to express my integrand in terms of polar coordinates. So remember that my integrand was 3x. X is equal to r cosine of theta. So let's just indicate that. My integrand was 3x, and I use the fact that x is equal to r cosine theta. And I've got to replace dx dy, or the area, infinitesimal area. And remember that for polar coordinates, that's given by r dr d theta. So there's an extra factor of r in there that we always have to remember to keep in. And I've written that in the order that I want to do the integral. The inner integral is with respect to r, and the outer integral is with respect to theta. Okay, so now I'm ready to do this integral. Carrying out the r integral, let's tidy the whole thing up a little bit. We have 3r squared cosine theta dr d theta. So I picked up that extra factor of r, and it's appeared as a squared here, r squared. So that r and that r combined. Okay, so now I can do this integral. Treating theta like it's a constant, which means that cosine theta is being treated like it's a constant. I'm going to integrate 3r squared to get 3r cubed divided by 3. Cosine theta is treated like it's a constant, and I'm going to be substituting in r is equal to 0 to r is equal to 1. Okay, so we have cancelling those factors of 3. Substituting in r is equal to 1 and r is equal to 0. We're going to get 1 cubed minus 0 cubed times cosine of theta. Or simply integral from 0 to pi over 2 of cosine of theta d theta. Cosine integral of that is sine. from 0 to pi over 2, which gives me sine of pi over 2, which is 1, minus sine of 0, which is 0, which gives me my answer 1. So you see we get the same answer as we did for Cartesian coordinates, as we must, because the integral is the same. It's just the method of integration has changed. We use polar coordinates. And when we use polar coordinates, we had to be careful to figure out what the appropriate limits of integration were for both r, going from 0 to 1, and theta, going from 0 to pi over 2. And when I set up my integral, I needed to remember to replace everywhere x and y appear in the integrand with the corresponding terms for r and theta. So x was replaced with r cosine theta. And the last thing I needed to remember to do was to replace dA, or dx dy, or dy dx, with r times dr d theta. And that extra factor of r is absolutely crucial. Once I did that, the integral itself was very straightforward to do. So let's look at another example where I'm going to start off with a Cartesian integral and I'm going to convert it into a polar integral and calculate it. So looking here at example 5, I'm given a Cartesian integral. I need to figure out what the region of integration is, convert that to polar coordinates, and then evaluate the integral. So let's take a look at what the region of integration is in Cartesian coordinates first. So my region of integration, let's put down the limits of integration, sketch those in the xy plane, and convert them into polars. So we're told that, looking at our integral here, x is the inner variable of integration, so it's going from y to the square root of 1 minus y squared. Y is the outer variable, it's going from 0 to 1 over root 2. So y is the outer variable, it's going from 0 to 1 over root 2. X is the inner variable, it's going from y to square root of 1 minus y squared. So it's worthwhile thinking about what those curves look like. I can even write them out explicitly. So we're going to be drawing the curves y is equal to 0, y is equal to 1 over root 2. I'm going to be drawing the curve x is equal to y, which of course is just the straight line, y is equal to x. And I've got the curve x is equal to the square root of 1 minus y squared. Well, that's actually just the unit circle in disguise. If I square both sides, I would get x squared equals to 1 minus y squared, which gives me x squared plus y squared is equal to 1. So this last limit of integration is actually just the unit circle. So it's good to notice that. So let's sketch what this whole thing looks like in the xy plane. Now I don't know in advance whether or not this is going to be in the first quadrant or not, so I should be careful here. Here's x, here's y. Here's x and y. We want the curves y is equal to 0, y is equal to 1 over root 2, y is equal to x, and the unit circle x squared plus y squared. So if I was to sketch all of those things, let's put them in red. I've got y is equal to 0, that corresponds to the x-axis. It's the curve y is equal to 0. I've got the curve y is equal to 1 over root 2, that's somewhere up here. I've got the unit circle, so that would be, here is just the first part of the unit circle, the first quadrant. So that's x squared plus y squared is equal to 1. And the final piece is x is equal to y, or y is equal to x. So that's a straight line with a slope of 1. And it's all passing through this point and this point. So this point down here is 0, 0. The point up here is going to be the point 1 over root 2, 1 over root 2. So we need to figure out what the region is of integration. And you can see that there's actually only one part of this, one little pi wedge down here, that's completely enclosed by these curves. But again, we can always figure it out by reading through the instructions. So it's telling us to pick a value of y between 0 and 1 over root 2. Pick a value of y between 0 and 1 over root 2. So for example, this value here. And to draw a little tracer until I get to the curve x is equal to y, and then shade that in until I get to the curve x is equal to the square root of 1 minus y squared, which we saw was actually just the unit circle. So it's very clear now that the region of integration is this pi wedge right here. Now, clearly this pi wedge has some nice circular symmetry, so it's going to hopefully become much simpler when I express it in terms of polar coordinates. So let's do that. You can see that if I was to express this in polar coordinates, I'm going to draw it in blue on top of this, then I would have values of r going between r is equal to 0 and r is equal to 1, so the unit circle. And I would have values of theta going between theta is equal to 0 and this line here, which is actually just theta is equal to pi over 4, so 45 degrees. So my limits of integration in terms of r and theta, let's do theta then r, are very simple. For theta, I'm going from 0 to pi over 4. And from r, I'm going from 0 to 1. So let's set up my double integral. I'm going to do the r integral first, inner integral, and then the theta integral, outer integral. Although it doesn't matter too much because my limits of integration don't depend on each other. My integrand was x, so remember I'm replacing everywhere I see x and y with the corresponding expression in terms of r and theta. So that was x here. And I also need to replace dx dy, so that was given by r dr d theta. Very important to have that factor of r in there. Let's rewrite that now. We're going to get r squared cosine of theta dr d theta. Carry out that r integral right away to get 3r cubed, r cubed over 3 cosine of theta, so treating theta like it's a constant. We're going to go from r is equal to 0 to r is equal to 1. From r cubed, so that's 1 over 3, so 1 cubed, cosine of theta, d theta, and I've given you the rest of that calculation there, the integral of 1 over 3 cosine theta d theta from 0 to pi over 4 is 1 over 3 root 2. So you can see that the challenge of this problem was actually figuring out exactly what the region of integration was. We were given it in terms of Cartesian coordinates. Took a little bit of sketching here to figure out that it was this pi wedge. And once I knew that, it was very straightforward to figure out what the appropriate limits of integration were in terms of polar coordinates. I could then construct my polar coordinate integral and carry it out quite quickly. Let's look at another example where polar coordinates make my integral very straightforward. So we're asked to calculate the integral of 2xy dy dx, where omega is the region in the first quadrant between the circles of radius 2 and radius 5. So you can see that there's very clearly circular symmetry here. First quadrant, we're going to draw two concentric circles, one of radius 2. Just looking at the first quadrant of each, and one of radius 5. So let's do something like that. This is a radius 2 circle, so this is x squared plus y squared is equal to 2 squared is equal to 4, and x squared plus y squared is equal to 5 squared. Or we could just think about it as radius is equal to 2 and radius is equal to 5. Now we're in the first quadrant, so we're going to be going between the y-axis and the x-axis, so we can sketch those as well. And let's draw what the limits of r, the distance from the origin, and theta, the angle subtended with the x-axis, are. So the limits for r are going to go between r is equal to 2, the inner circle, and r is equal to 5, the outer circle. And for theta, we're going to go from theta is equal to 0, the x-axis, to theta is equal to pi over 2, the y-axis. So let's write down what those limits of integration are. Theta is going from 0 to pi over 2, and r is going from going from 2 to 5. R is equal to 2 to r is equal to 5. So what does our integral become? We've got the integral, we're going to do the r integral first, so 2 to 5, and then the theta integral, so 0 to pi over 2. Our integrand was 2 times x times y, so that's going to be 2 times r cosine theta sine r sine theta. So that's my 2 times x times y. And we've got dy dx, so expressing that in terms of r and theta has r dr d theta. So once again we have that extra factor of r. Okay, so now let's rewrite this expression slightly. Integral from 0 to pi over 2. Integral from 2 to 5 of 2 cosine theta sine theta r squared, r cubed in fact, dr d theta. Ran out of space there. That's 2 cosine theta sine theta r cubed dr d theta. So I'm ready now to do the integral with respect to r. I can actually simplify things as well by using the fact that 2 cosine theta sine theta is sine of 2 theta. I can use that. Doing the integral with respect to r is going to give me r to the power of 4 over 4 from 2 to 5 sine 2 theta d theta. Substituting in r is equal to 4 and r is equal to, r is equal to 2 and r is equal to 5. It's going to give me 5 to the power of 4 minus 2 to the power of 4 all over 4 sine 2 theta d theta. And if you carry out the rest of that calculation yourself, you'll find that the answer is 609 over 4. So this integral was a very straightforward integral to do. In polar coordinates, it would have been quite complicated to figure out what this would be in terms of Cartesian coordinates. Let's look at another example now where we have polar coordinates but with limits of integration that can depend upon one another. So let's look at example 7. So I have a region that's bounded by a curve r is equal to 2 cosine of theta. We're going to sketch this and then use it to evaluate this Cartesian integral. Now we saw in example 3 actually that the curve r is equal to 2 cosine of theta was given by the Cartesian expression x minus 1 all squared plus y squared is equal to 1. Or more, or to put it another way, it's a unit circle centered at 1, 0. So if I was to sketch what that curve looks like in the xy plane, I'd get something that looks a bit like this. So here's y, here's x is equal to 1, and the curve r is equal to 2 cosine of theta is going to correspond to a unit circle centered at x is equal to 1. So it just touches the origin, it just touches this point here, but it's entirely on the right hand side. Now we want to express the limits of integration of this in terms of r and theta. So let's first of all sketch what we mean by the region of integration here. So this is the region of integration shown in green. And we're going to express this now in terms of polar coordinates. Now remember, the polar coordinates are stuck at the origin. I can't, unfortunately, put them at the origin of this circle or the center of this circle, but that's actually going to be okay. So we've got theta, I've got r, and I can write down my limits of integration for r and theta. So thinking about r, we can see that the r is going to start off at r is equal to 0. And it's going to end when it gets to this purple curve here. And that purple curve is given by r is equal to 2 cosine of theta. So the limit of integration for r, the upper limit, is going to be r is equal to 2 cosine of theta. So in fact the limit of integration for r depends on theta, depends on what direction you're pointing in. And that makes sense. If I was pointing directly horizontally, that is when theta is equal to 0, r would go from 0 to 2 times cosine of 0, so it would go from r is equal to 0 to 2. But if it was pointing at an angle, it might be smaller than that. So what are the values of theta that we can take? Well, it can take values horizontally, it can take values pointing directly downwards or directly upwards. So what is the value of theta directly downwards? Well, it's going to be theta is equal to minus pi over 2. And when this thing is pointing directly upwards, it's going to be theta is equal to pi over 2. So 90 degrees down or 90 degrees up. So let's write down what those limits of integration are. I've got theta going from minus pi over 2 to pi over 2, and I've got r going from 0 to 2 cosine of theta. Now, this is a different situation to the ones where we've seen before, where it doesn't matter what order of the integral I do in terms of r and theta, because the limits of integration didn't depend on each other. In this case, it does matter, because r has a limit of integration that depends upon theta. And we saw that that is only allowed if I have my r integral first. So these limits of integration are actually telling us the order of integration. So r can depend upon theta, which means it has to be the inner variable. And theta is just constants, so that's okay. That's going to be my outer variable. Let's take a look at what the actual integral is we're trying to do. It's 3 over the square root of x squared plus y squared. Well, that's quite nice because 3 over square root of x squared plus y squared in polar coordinates is just 3 over r. So using here the fact that r is equal to the square root of x squared plus y squared. And we've got dx dy, so that was r dr d theta. And remember, of course, that I've got to match the order to the limits of integration. So my inner integral was with respect to r, so r is first. My outer integral is with respect to theta, so theta is second, the outer integral. So now I can do this integral. I can actually cancel out the factors of r, do the integral with respect to r to get integral from minus pi over 2 to pi over 2 of 3 times r, going from r is 0 to 2 cosine of theta times d theta. So substituting in, we're going to get 6 cosine of theta minus 0. Integral of cosine of theta is sine. From minus pi over 2 to pi over 2, which is going to give me 6 times sine of pi over 2, which is 1, minus 6 times sine of minus pi over 2, which is minus 1. So the answer is 12. Now, when we calculated the infinitesimal area dA in terms of r and theta, we saw that we picked up this extra factor r, and that was really important. It told us how we had to change the infinitesimal area depending on where in the r theta coordinates we were looking. Obviously, in terms of Cartesian coordinates, that infinitesimal area doesn't change. It's just a square everywhere. Now, how would that change for a more general coordinate system? This is given to us by something called the Jacobian transformation. It's not something that we'll test in this course, but it is a powerful technique, and it actually tells us where the polar coordinate formula comes from, so it's worthwhile seeing. So if I was to have completely general coordinates, let's call them u and v. So we could almost imagine drawing a line like that. That's u, and this is u plus du. Think about these like longitude and latitude. Or radius and angle. Or in terms of spherical polar coordinates in 3 dimensions, you could have radius and angle in 2 directions, declination and right ascension. Okay, so that's one coordinate, which I'm calling u. And everywhere along this line here is got a value of u. And I can shift over by a little bit and get another value, du. Let's think about the other coordinate. We'll call it v. And let's say it's doing something like this. So we'll call this line here is v, and this line here is v plus dv. You can see that these 4 lines fill in a region here. And this is an infinitesimal area dA. So you could think again about this in terms of polar coordinates, where u could be r and r plus dr, and v could be theta and theta plus d theta. So what is the area enclosed by those 4 curves? Well, the way we're going to do that is by using something called the Jacobian transformation, which allows me to transform from one coordinate, let's say x and y, to another coordinate system, u and v. And all I need to know is how u and v and x and y are related to one another. So the way that we do that is by calculating this determinant. It's called the Jacobian determinant. And notice that it involves the derivatives of x and y with respect to u and v. So if I calculate dx du, dx dv, dy du, dy dv, I form this determinant. So as a specific example, imagine we're looking at the polar coordinates. So x is equal to r cosine of theta and y is equal to r sine of theta. This Jacobian determinant is going to be given by partial derivative of x with respect to r, partial derivative of x with respect to theta, partial derivative of y with respect to r, and partial derivative of y with respect to theta. Or multiplying out that determinant, I get dx dr, dy d theta, dx d theta, dy dr. Now I know what x is and y is as functions of r and theta, so I can actually calculate what these partial derivatives are. dx dr is just cosine of theta, dy d theta is going to be r cosine of theta, and I can do likewise for these expressions here. And you notice what I get is cosine theta r cosine theta, r sine theta, or if I take out that common factor of r, I get r cos squared plus sine squared. So I just get r. Now the Jacobian determinant tells us exactly the term that I need to put in front of du dv to get my new coordinate integration. So for polar coordinates going from dx dy to dr d theta, I need to multiply by a Jacobian determinant, j, that's equal to r. So it's exactly that extra factor of r. Now what the Jacobian determinant is telling us is how much is that infinitesimal area changing as I move around my new coordinate system, u and v, or in this case, r and theta. Now we're not going to deal too much with other coordinate systems in this course. We're only going to focus mostly on the polar coordinates and the Cartesian coordinates. But there is, in example 8 here, a little challenge problem for you to think about how you might calculate double integrals, or in this case triple integrals, in terms of the spherical polar coordinates. So how would you replace dx, dy, dz, that is a triple integral, infinitesimal volume, in terms of polar coordinates? And you're going to use the Jacobian transformation to do that. This is an optional challenge problem for you, and we'll discuss it on the help forum.